Next, we have Thomas Reynolds with a talk about energetic nuclear transients in luminous infrared galaxies.
Okay, hello. Can people hear me and see my slides?
Yes.
Fabulous. Okay, yes. Hi, yes, I'm Tom. And yeah, we're going to be talking about these nuclear transients that we're discovering in these luminous infrared galaxies. So first then, what are these luminous infrared galaxies? It's a nice example of one here on the right. It's known as the bird. I guess you can probably see why. These things we define as luminous in the infrared, more luminous than this 10 to the 11 solar luminosities, or for ultraluminous infrared galaxies, another order of magnitude more luminous, so LURGs and ULURGs. Why are these things so luminous in the infrared? They're dusty. This dust is heated up by starburst, young stars, or an AGN, or both, often both, and then that produces the infrared luminosity that we see. Many of these things are interacting or mergers, which you can kind of see from this example, and they have very high star formation rates from these starbursts and can produce many supernova per year, core collapse supernovae. And these have been the subject of supernova searches for these obscured supernovae, and you remember they were discussed a little bit in Jacob Jensen's talk yesterday. So moving on from that little intro on these galaxies, onto the actual transients then. So there's a little story here about these dust-obscured nuclear transients in these LURGs that begins with this transient called ARB299b81. And this was discovered all the way back in 2005 in a near-infrared search for dust-obscured supernovae in these LURGs. It's a really long-lived transient in the infrared. It's actually still going today, as we'll see in a little bit. You can see a light curve in the bottom right from some Spitzer and NOT data. So it's radiated a lot of energy. So the really one of the really interesting things here is that this thing is not luminous in the optical or the X-rays. So it's very heavily obscured. And the evolution of this infrared data is consistent with an infrared echo from dust. So we've just had a really nice explanation from Stuart about this. So you remember his very nice diagrams for the scenario here. And so and as he mentioned, it's very difficult to say what the underlying flare that's producing an infrared echo is without more data. But here we have a really nice smoking gun for what this thing is in this resolved radio jet that was observed with this transient. It's shown in this bottom panel here. And you can see there was some, in 2005, there was just some emission, some compact emission that then faded there and then moved away from its original location. And this radio jet in particular is at an angle that's inconsistent with known Seyfert-2 AGN that's hidden inside this galaxy nucleus. And therefore it provides a really strong case for some new accretion, which is of a star, a tidal disruption event, as we heard about in the last talk. So what's the takeaway then? Maybe there's some sort of population of TDEs that's completely hidden in optical and UV and X-rays and can only be detected in the infrared, in particular, perhaps in these luminous infrared galaxies. Well, one event does not make much of a case for it, but this is not the only one, as I'm sure you guessed was where I was going. So I can't go into all the details here, but on the left, there's this luminous transient in this ULURG with this long name. You can see on the left there. And this thing was actually discovered in optical spectroscopy. I'm showing the discovery spectrum here. This just, again, kind of highlights this was like a surprising fortuitous discovery. This guy has rather debated nature. There's a lot, I'm not going to go into this, but there's a lot of citations there in the bottom left if you're interested, or as to whether this is a TDE or an AGN-related flare, this whole issue of imposters that, again, Stuart mentioned in the last talk. One interesting little wrinkle is there's evidence for a double AGN in this galaxy. But anyway, moving on from this one, there's also AT2017 GBL. So this transient is a little more similar to the first one I mentioned, because it was discovered again in a search for obscured supernovae in a LURG in the near infrared. Again, it's luminous in the infrared and the radio, but faint in the optical. We found in this paper, Cool 2020, that TDE is the most plausible explanation. I'll cover a little bit why a bit later. But the really important thing perhaps to mention then is that because this was part of a supernova survey, we were able to nail a rate onto it for these events. And we found, some pretty high number, maybe 10 to the -2 of these things happening per lerg per year, but with some pretty large uncertainties. So that motivated the kind of work that's the primary focus of this talk, which is to go look in the Neowise data, again, mentioned in the last talk. So this is nice mid-infrared observations at 3.4 and 4.6 micron over a long period of time with a nice regular cadence. So it's really good for detecting these infrared echoes. So we grabbed a sample of lergs from the Sanders catalog. We've got kind of 200 Galaxy systems, and then we can resolve a few of their separate nuclei. And then we just looked for large changes in luminosity, just kind of taking the maximum and the minimum luminosity, setting this energy constraint, and then filtered out a few obvious stochastic varying kind of light curves. And what we ended up with is 5 of these luminous transients, so 2 of them the previously mentioned, and then 3 new ones. So here's the family. In the left, we've got the W1 3.4 micron observations. On the right, the 4.6. This is in luminosity space with the host subtracted. So again, you can see this ARP299 transient I mentioned, and there's a lot of Spitzer data shown here, and then also the WISE data, the more recent stuff, and it's still not quiescent after, 17 years or something. And then on the other end of things, the green points showing 2017 GBL, which is much more short-lived and less luminous, and then these 3 new objects. Not going to go into kind of the individual objects in great detail, but one in particular is interesting because it's still rising now, so we're going to be getting more WISE data, and we're also doing more follow-up in the near-infrared, for example. We've actually detected some radio variability, and we're going to continue follow-up and see what comes of this transient. So what can you do to these things? Well, first we wanted to check to see if they're consistent with infrared echoes. You can fit black bodies to the 2 WISE points that you have. You get some pretty large uncertainties, of course, but it does work quite well in terms of giving you temperatures that are consistent with infrared echoes from dust. So they start out about the sublimation temperature from dust for the dust, and then evolve smoothly, cooling over time. And you can check this method against some of these previous works that have a bit more data, and it's very consistent within the quite large uncertainties. And then you can, of course, calculate luminosities to actually work out how much energy is in these things. And so you can work out a total radiated energy. And these things have quite large energies from about 10 to the 51 to 10 to the 52 plus ergs. You can compare these to like a very luminous mid-infrared supernova, such as 2010 JL. I guess the most luminous mid-infrared supernova, and these things are considerably more luminous than that. So it seems unlikely that they're just supernova hiding, even though these are very galaxies with very large supernova rates. And then you can kind of compare them to some TDEs. There's 14 Li, which is a kind of a normal TDE, whatever that means. Had a rather not super strong infrared echo, presumably because this dust covering factor was somewhat low. And then there's this 15 LH that was mentioned again by Stuart in the last talk, which actually has energy that's kind of in the ballpark for our transients that we see here. So maybe it's, and that is kind of a more weird object, so maybe it fits in with these a little better. So a bit more about the physical scenario. Both for this ARP299 transient and for 2017 GBL, we came up with the scenario in the top left for what was actually occurring. We perform a radiative transfer modeling on the SED of these galaxies to try and see the contribution of the starburst and the AGN, and we find obscured type 2 AGN inside these galaxies. So there's some dusty torus there, which is going to have very high extinctions in the line of sight, or cause very large extinctions in the line of sight. So this explains why it's very difficult to see and detect anything in the optical. So then we argue that the little optical emission we see and the actual infrared echo is coming from some polar clouds that are sitting above the AGN, kind of the dusty torus. And
3 minutes.
Okay, thanks. And so this is the origin of the emission that we see. And this is supported by the fact that if you include the transient flux in the SED fit, you can just turn up the polar dust component, and it makes your SED fit work quite well. As you can see, this is what this bottom right plot here is showing. So back to this issue of rates then. Our survey updating the rates comes up with these new numbers, 10 to the minus 2.3 to 10 to the minus 2.8 transients per year. So still a large number. Here I've just got a few kind of non-representative examples of some other rates for these things. TDE rates in optical are 10 to the minus 4. So if these things are TDEs, then there's a highly elevated rate in these galaxies. There's also this interesting Mirong survey of just lots and lots of, I think it's 1 million galaxies with WISE data, and they found a much lower rate. But so it's not inconsistent for these things to have a higher TDE rate in these galaxies. They're mergers, they can have dual supermassive black holes that could influence the TDE rate. And there's also this issue of enhanced stellar densities that, again, Stuart mentioned, which, you've got lots of star formation and disturbed stars, so you can get this in the nuclear regions of these systems. So I thought I should address a little bit this issue of imposters. Are these things not TDEs at all? And the short answer is, well, in most cases, it's hard to tell. In R299B81's case, the radio jet provides this compelling evidence, but in other cases, it's more difficult unless you really have that multi-wavelength follow-up. Certainly, supernovae seem unlikely, and there are some arguments that even some of these changing look AGN are not so consistent with what we see, particularly because they show some multi-year optical variability that we can rule out in some of our cases where the infrared evolution is short. So finally, the kind of implications of these things. So optically discovered TDEs have these known selection biases, or at least have had, towards things that don't have an AGN and objects that don't have dust, just because, as Stuart says, there's been this effort to probe quiescent supermassive black holes and also to remove contaminants from your sample you're classifying. And also, given the TDEs are very blue, people look for very blue transients, so that if you introduce a little extinction from dust, maybe objects don't get classified. Whereas our transients here, they're all occurring in AGNs, or at least there's some AGN there, and they're all occurring in regions with lots and lots of dust, to the point where you can't see it in optical at all, as I've said. And it could be the case that these things are intrinsically different because of some interaction between the AGN disk and the TDE. There's been a little bit of work on this, and it's certainly the case that we're getting a much larger covering factor of dust, and so we're really probing the actual energetics of the underlying event. So my kind of last point is, my last point is just that optical surveys are going to keep missing these things. So even things that go much deeper than the surveys that exist now. There's a real opportunity for Roman which is going to be able to detect all of these dust echoes in the local universe, as Stuart mentioned, to actually discover these things and really characterize them well. So I think I'm nearly out of time, so I'll just leave you with a conclusion slide there.
Great. Thank you, Tom, for a great talk. Folks, if you have questions, you can post them here or in Slack. And while you think about that, I actually have a question. Tom, in the light curves you showed for some of these, there seem to be different sort of two families of timescales. Some are relatively quick, and particularly ARP299B is a little slower. Can you say a little bit about how I should think about that, or how you think about that?
Yeah, so something to do with the dust geometry and the scale of the dust, I think is the basic point. I think you need to do, and then obviously the actual underlying flare itself could be different depending on the object. There's the initial flare that can produce an infrared echo, but then there could be some ongoing input from this kind of later time emission from the TD as well. But yeah, I think you need to do some more kind of self-consistent modeling, which we'd like to do, but the issue is you kind of need some optical light curves to put in, which are not detecting. So it's a little tricky, but it's something we're going to look a bit more at in the future. And then there is also the possibility that, as I say, we're not, like, maybe some of these are TDEs and they're one family, and then there's a few contaminants in here that are different kinds of flares entirely.
Yeah, thank you. We have one quick question from Lee Armis on Slack. It says, thanks, Tom. Can you go over the comparison to the supernova luminosities again? Are they all way above the supernova luminosity, or is it only 05189?
So in terms of, this is like the total radiated energy is, I think, the best thing to think about. So the total energy radiated by 10 JL is this number here. And then the total energy we get out of these objects just by kind of integrating, you know, under the luminosity over time, are these numbers in the top here. And these are kind of lower limits because, you know, not all of the energy is going to be coming out in the infrared in the case of these transients. So yeah, I think you just don't have enough energy, even though the luminosity, the instantaneous luminosities might be higher for supernova. You don't have enough energy over the total light curve to match these transients, if you understand me there.
Great. All right. Thank you again, Tom, for a great talk.
Thank you.